One of the most critical aspects of black holes is the information they provide in regards to Einstein's theory of general relativity. Not only that, but it lends to our understanding of physics, both here on Earth and out in the cosmos as well. In simple terms, the theory of relativity says that time can be slowed down or sped up, depending on how fast an object is moving at extreme speeds near light waves. Thus, if one were to theoretically visit a black hole and fall through the event horizon, while another person observes from afar, the time for the person falling would slow down dramatically compared to the observer. In fact, estimates would put the time for the falling man to slow down to nearly infinite measurements, meaning the observer would live thousands of lifetimes before ever watching the falling person reach the singularity, or center of a black hole. Speaking of singularities, the centers of black holes are absolutely chaotic points in the universe on their own. It's theorized that as soon as something crosses the event horizon into the black hole, the object is actually stretched into an abnormal, oblong shape and stuck within the confines of the black hole for eternity. This is a concept called spaghettification, appearing exactly as it sounds. As for the center itself, the singularity is actually a microscopic point, so small it's beyond comprehension. Even with its small size, however, its mass is so large its gravity and density approach infinity, much like the time beyond the event horizon. Due to the insane measurements of gravity and density, the only possible outcome of something entering a black hole is being ripped into oblivion. While immediate and total annihilation isn't necessarily an observed fact, it's hard to imagine any other likely scenario in a place where the laws of physics are completely left void. Hearing about the destructive forces of black holes and the horrifying, hypothetical centers that await anything that passes through makes people imagine black holes as beasts of nature with vacuums that suck in everything within hundreds of light years around it. However, this isn't necessarily the case. While black holes do function as a vacuum and feature a point of no return, they are not just wandering around the universe sucking anything it can. For example, if the Sun was swapped out with a black hole and contained the same amount of mass, the Earth would continue to orbit around the central star like normal. In most cases, matter enters a black hole from the stellar winds of their companion stars, forming an accretion disk around the black hole before slowly but surely making its way past the event horizon. Accretion disks aren't just slow swirling victims-to-be of their hosts. Rather, they also function as incredible sources of energy, powering black holes more efficiently than our Sun and most stars across the galaxy. The area between the event horizon of the black hole and the innermost layer of the accretion disk is called the fringe, where matter orbits the black hole the quickest due to a stronger gravitational pull. Before it can cross the event horizon, however, the inner accretion disk begins moving so fast it creates a level of heat that exceeds 1 billion degrees Fahrenheit. The ensuing energy is so great, mass from the disk transforms into a type of radiation called black body radiation. This ratio of total mass converted to energy is a whopping 10%, compared to the next most powerful energy source in nuclear fusion at 0.7%. Like anything both on Earth and in the cosmos powerful enough to create the energy seen by black holes, scientists are never short of ideas on how to harness the aforementioned power. In terms of black holes, one of the most exciting propositions thought up by astronautic engineers is the use of accretion disks to power spacecraft for interstellar travel. This theoretical plan, labelled black hole starships, was first proposed by Arthur C. Clarke in his book Imperial Earth, and another work by Charles Sheffield. It wasn't seriously considered by the astronomical community until 2009, when Louis Crane and Sean Westmoreland developed the theory. They proposed that it could be possible as long as they could create an artificial black hole, paired with a parabolic reflector to reflect the radiation. This theory requires 5 separate criteria, including a mass equal or similar to a starship, a long enough lifespan for the black hole, enough power to accelerate at a fraction of a speed of light in a quick time frame, a small enough size to gain the energy needed to create it, yet a large enough size to focus the energy. Of course, the laws of physics on Earth make realizing this plan next to impossible, as the amount of energy and radiation from a black hole of any size would most likely be too great to reflect with the resources we currently have. As the future sees constant evolution in technological and scientific advances, never say never. When you close your eyes and imagine a black hole, you probably think of something so massive it's beyond comprehension. It's for good reason too, because in most instances, black holes are bigger than the human brain can make sense of. That being said, not all black holes are as big as you've been led to believe. In fact, black holes theoretically could be so tiny they constitute the smallest known objects in the observable universe. These objects are usually described as measuring at Planck's length, which is widely agreed upon as the smallest possible size or measurement realistically attainable by human observation. Currently, scientists are attempting to create their own artificial black hole on a quantum level, aiming for a black hole measuring just a bit bigger than Planck's length, at around 10 to the power of -20 in grams. Another typical assumption about black holes and how they are created is that they all must be formed through the death of a star, and a star alone. The fact of the matter is, in theory, a black hole could be created from anything, and not just the massive celestial bodies entering the end of their lifespan. For example, if one were to harness the ability to take our current sun and shrink it to the size of an object just 6 kilometers across while retaining the original mass, the density would be so great it would form a black hole as we understand them. The same could be said for Earth. Reduce the size to a comparably tiny measurement, retain the mass, and voila, you have a theoretical black hole. The problem is proving this theory is all but impossible on a macro scale. There is no means to shrink planetary objects or entire stars into such minuscule versions of themselves just to see what would happen. It's all based on theories and calculations alone. Thus, as of now, the only possible way for a black hole to form is the collapse of gravity during the death of a star, usually 20 times larger or greater than our own Sun. One of the coolest individual black holes comes 1.8 billion light-years away and goes by the name XJ1500 plus 0154, abbreviated as 154. The black hole was discovered back in 2005 when researchers studying the Chandra X-ray Observatory telescope aboard the spacecraft Columbia noticed a massive X-ray flare from the direction of 154's host galaxy. The flare was first recorded on Chandra's twin telescope, the XMM Newton, from an optical lens capture. When the same point was captured by Chandra's X-ray vision, the light emanating from the star showed up 100 times brighter. It didn't take long for researchers to realize this was the effect of an incredibly enormous star exploding into its final stages, consumed by the black hole 154 at the center of the host galaxy. 154 was calculated to be a supermassive black hole, and all signs suggested it had been consuming the former star for a long time, as long as 10 years in early estimates. In fact, the destruction had been happening for so long on such a massive scale that the radiation produced from the accretion disk surpassed what's known as the Eddington limit. The Eddington limit is the balance of which the outward pressure of the radiation equalizes with the gravity's inward pull of the black star. Now that researchers have found a prime example of these limits being tested, more can be understood about what happens when the Eddington limit is passed, and how there are black holes with a mass billions of times larger than the Sun when the universe was merely 1 billion years old. Who knows, maybe Black Hole 154 will devour its star for the rest of eternity, creating energy and radiation beyond any measurements recorded thus far in human history. If you were to ask the average person on the street what is located approximately at the centre of our Milky Way galaxy, most folks would either say they don't know, or guesstimate and claim our solar system is the central body. In reality, scientists have learned in the last 40 years or so that a supermassive black hole, called Sagittarius A star, is actually the behemoth residing at the centre of the galaxy. The black hole was first discovered by way of radio signals in April of 1933 and labelled as an ultra-bright radio source in the 1950s at The Ohio State University in Columbus, Ohio. By the 1980s, it was widely agreed upon by the astronomical community that whatever bright body sitting at the Milky Way's nucleus was probably a black hole. This was confirmed in 2022 when the Event Horizon Telescope was able to capture the light from the accretion disk using aperture synthesis from radio data collected since 2017. While the thought of a black hole residing in our own galaxy may be a scary thought, never fear, Sagittarius A star is located just under 26,000 light-years away from Earth. It may seem like a close distance compared to the rest of the universe, but is still far enough away to prevent any light from escaping the gaseous chamber enveloping the black hole. Previously, we mentioned that black holes aren't exactly sucking everything and anything in their paths across the universe, and only vacuum in the matter directly surrounding its gravitational pull. Most people believe that once you're in the accretion disk, that's the end of the line for whatever object might be so unlucky. However, studies have shown that might not be 100% accurate. While we've never recorded something entering a black hole and coming out the other side, there has been recorded instances of chunks of matter slipping away from the fast-moving inner accretion disk moments before crossing the event horizon and jettisoned into space. This has been best seen with Sagittarius A star, the aforementioned supermassive black hole. It's known for its occasional spitball, a euphemism for the collected chunks of matter that escape the accretion disk and form a ball only to be flung by the power of the black hole at upwards of 20 million miles an hour. So while there is no prediction for Earth to be swallowed by a black hole, the odds aren't zero at one day having a spitball fly by our solar system at blazing speeds. Thanks for watching Access Astronomy. We hope to see you here next week for another video.